If you open a book on Oracle, or take a look at the Oracle Concepts Guide, you are likely to encounter a diagram that looks something like this, that outlines the major memory structures used in Oracle. This diagram is actually a simplified version of the diagram that is found in the Oracle documentation, but it includes the most important pieces that we need to understand as developers. You can roughly divide the memory used by Oracle into two sections. The first section is the System Global Area, or SGA as it's often referred to. This is a memory structure that is shared across all users and all processes in Oracle. So when you hear SGA, think of data that can be shared and reused amongst users and processes. The second section of memory is the PGA, or Program Global Area. The PGA is memory that is dedicated to each individual session or current login in Oracle. When you hear PGA, think of data that is private to a login session, because each segment of memory in the PGA is dedicated to a particular login session. Of these two, the amount of memory devoted to the SGA is typically much larger. To give you an idea of the size of an SGA, oftentimes the SGA will use 80% or more of the amount of physical memory on the Oracle database server. So if your Oracle server has 96 gigabytes of RAM, you may very well have an SGA size of 75 or 80 gigabytes, which at least at the time of recording of this video is a very large memory structure. The amount of memory used by the PGA is much smaller, but can become a concern if you have very large numbers of sessions that connect to Oracle. So as developers, we want to design applications that efficiently manage our connections to Oracle so we aren't wasting memory on the Oracle server. The three most important areas of memory in Oracle to understand as a developer are the buffer cache, the shared pool, and the PGA associated with each login session. So in this section, we'll concentrate on understanding how these three memory structures work. As developers, when we are writing SQL, we most often think in terms of rows. How many rows is my query going to return? I need to insert this many rows into the table, or how many rows did my delete statement impact? Rows are important to Oracle as well, but Oracle is really working in blocks. A data block is the smallest level of granularity that Oracle will store data in. Block sizes can range from 2 kilobytes to 32 kilobytes, with 8 kilobytes being the default size. When you think of a block, think of it as a container for data. A block can contain data for either a table or an index, but it is probably easiest to understand if you think of a block that contains table data as is shown here. Each block is going to have a block header, which is going to contain some administrative data about the block, like if this is a table or an index, what is the name of the object that the block contains data for, and a directory of rows contained in the block. Typically, the block header is going to take somewhere around 100 bytes, sometimes a little more, sometimes a little bit less. The rest of the block, if this is a table block, is going to contain the data for the rows contained within the block. As shown here, each block will typically contain many rows, oftentimes hundreds or even thousands of rows. So what Oracle is doing is trying to first locate the block that your data is in, and then locate the row inside of the block. You also notice in this diagram that there are some gray areas within the block, and those represent free space. When you create a table, you can use the PCT_FREE and PCT_USE parameters to control how much free space is left in a block. But generally, it is a good idea to have some free space for a couple of reasons. First, we might update a row, and as a result of that update, the row may take up more space. If we have some free space at the end of the row, then the row can simply expand into that free space. If we didn't have any free space, Oracle would have to move this row somewhere else in the table, maybe to a different block, and that would cause additional I/O operations to occur, so that isn't very efficient. Second, having some free space at the end of the block allows some room for Oracle to insert new rows as they are added. Later in this module, we'll talk about the performance metrics of logical I/Os and physical I/Os. Both of these metrics are reported in terms of blocks read. For now, though, let's look at how Oracle reads the data that it needs to.